continue. So, as I mentioned, one key technology change that has happened over the last, again, 5-6 years, and which is now looking promising, and I think this is the way it will go forward, is known as 3D integration. So how do you build a memristor, right? So, or a resistor RAM. So it's basically, now you have to think about how are we going to put it in a compact 3D system. So one way to do it is basically to think about backend interconnect. You have two metals and you stick an insulator between them in the VR. And this is typically, so this is from some very seminal work done on this, and you end up seeing IV results, right? So now here is what I'm saying: different resistances. As the state of the RAM changes, you end up seeing different resistances. The reason you see a current like this is because it is in a log scale. And if you look at the conductance measured as a function of pulses, you're getting a conductance variation because of the change in pulses. There are different ways of making these resistors. Simple way, as I said, is using these 2D arrays where you have one metal running this way, that metal running the other way, and then stick an insulator between them. You can also think of it where we build the memristors along the finger and essentially have two kinds of, so one you put here, the other on top, and a filler between, which conducts the memristor. The third way is similar to the 3D NAND, where we have a 3D NAND array where there is a metal insulator and a metal on top. Right? And the fourth one is a CMOS architecture, which is most complicated to build because I mean there is no way to make this in silicon as of now today. But topologically, this will give you the highest packing density for the memristors. Also, remember that as things get complicated, as 2D scaling becomes harder, another way by which people are scaling technology is 3D scaling. So instead of having a single CMOS layer, you can think about CMOS layers which are stacked one on top of each other. And that's essentially how we plan on reducing the footprint of the chip going forward. So the ideal method would be you would have CMOS layers and then you would have these stacked memristors on top of it. Right? So here's another process. This is again being demonstrated at a lab level where you have multiple memristors connected on top of the CMOS lamp. And here is just before we leave this topic, this very nice work from MIT, which essentially worked on building an entire electronic system on a single wafer. So basically what you end up seeing is you have these multiple layers. You have basically silicon transistors at the bottom. Then you have a carbon nanotube logic array right here. You have an RAM layer on top of it. And then you have sensors, etc. on top. So here you basically have a chip which has sensors on top, followed by the memory layer, followed by the processing layer. Right? So the entire footprint of this, so entire 3D system sit on a simple footprint, and I believe this is the way we go forward, especially as you end up scaling technology. So here you see that you can get away with slightly slower transistors, if you will, because you have stacked them one on top of the other. Again, a very, very interesting paper if you want to read more about how to do this. So what are the general challenges in memory, in computer memory on your orbit, right? The biggest challenge today is ADC. So while we've worked on embedded memories, we've worked on architecture, ADC of the analog to digital converter is the basic bottleneck. Because today, the area of the ADC designs are pretty standard, and it's really hard to use the area of ADC. So ADC ends up becoming, and remember we have ADCs at the end of every column. So the column density is determined by the width of the ADC, right? And so therefore, if you reduce the ADC, you can stuff in more columns per unit area and end up having a tighter chip. And the other thing, as I said, is the variation, right? So as we looked at cell to cell, the on resistance varies. The variation in the transistor ends up having an offset in the ADC also. So because of this, that makes our design that more complicated. We can't really stuff more things. And the final thing to think about is, So far, when we're doing this design, and if you look at most published papers in this field, we talk about very small memory arrays, right? We're talking about kilobytes of memory arrays. As you end up processing a lot more data when you put data from the real world, you want to have a lot more memory. And for that lot more memory, it may not be possible to do everything on a single chip, which means that you need to have an access to a DRAM chip nearby. And so if you want to have larger memories, then access time to that chip might limit the performance. So we need to think about how to do that, because there is a limit to how much non-volatile memory you can put in a crossbar array before the crossbar array begins to malfunction. So for those interested, there is this very nice tool which is available on GitHub to do simulations on neuromorphic. It's free for all, so you can use it. It's used to do architecture simulations, device simulations, etc. So what are some of the other issues that are highlighted? So one problem today we have is we want the resistance of the RAMs to be very high. So because the problem is this resistance determines the current. Current determines power, right? And so you don't want a low resistance here. So you want a high resistance here, and that's not easy to achieve. The second thing is that the forming voltage that I told you about, the forming voltage is still very high with logic ETE. So if you want to stick this RAM on a logic chip, I need to have essentially level shifters so that I can do the forming first and then follow it up with operation. That means more area. So finding a material where the forming voltage is of the same value of VDD would be ideal. The second thing is the on-off ratio that we have achieved should be roughly around 10, which I think most memories have. Multi-bit operation, again, most memories are able to achieve that today. Now the other problem is right here, retention. Right? Stability of weights over large time are needed. And this can change. Now we have something known as initial relaxation. That is, once we form the device, when we're going to use the device again, there is a certain time period between which there is a possibility of drift. Right? So that ends up causing a variation in the resistance. And obviously you have read distance. Like any other memory, there will be read distance present in this network. So you need to be aware of that. And that's something which is not clearly understood. And so there's a lot more characterization that needs to be needed. Second thing is endurance. As I told you, endurance is pretty good enough for our application. So endurance is not a problem, but retention remains to be a big problem. And finally, the other thing is, I told you the requirement is I want a linearity in weight. Like that should be able to access. Suppose I want to do weight as a function of pulses. I want it to be a linear system. I can determine what the weight is by counting the number of pulses needed to get that weight. That's not always possible. So hence it's important to have materials which can do that. So this is a material problem, not so much an architecture problem. So I'd like to close this part of the talk by obviously highlighting that there's a huge compute challenge which is associated with AI. We believe computational memory, which can do computations locally, will play a key role. Expect resistive devices to be important, and there are certain challenges which need to be overcome for that. If you think about what an ideal compute system of tomorrow would be, I wouldn't say we'd be done away with CPUs. We will have CPUs, but the CPUs will be accompanied by GPUs with computational memory and four processors all together in a silicon chip. So which means that a silicon chip or package has to support not only one silicon logic chip but multiple architectures of the same chip. So how do you plan that? How do you do heat transfer? How do you ensure all the interconnections, etc. remains a challenge. Okay. So now I want to switch gears to a completely different topic, which is implantable electronics. So we spoke about machine learning neural networks. Now we switch to biology. Okay. So implantable electronic devices are not new. Most of us have either had it or know people who had it. Simple things like root canal, or when you put a new tooth, that's a implant, right? Or if you have people who have a orthopedic implants put in, that's an implant. we're talking about is implants with integrated electronics. Again, that we've had cochlear implants, retinal implants, prosthetic implants. And finally, we're talking about therapeutics, where we want to have targeted drug delivery, right? We don't want oral delivery. We don't want intravenous delivery. We want to ensure that drugs are delivered to specific target cells in the body. Now, what's the advantage of all this? The advantage that these have is basically, suppose using a sensor, right? Suppose you want to measure the sensor of, say, a heartbeat sensor, or you want to measure the blood pressure in a human being. Today we measure blood pressure of the artery here, but if you think there is a risk to the heart, having a blood pressure sensor directly next to the heart would be most convenient. It's directly next to the organ. It gives you the most accurate data, if you will. So there is a certain advantage to having implanted electronics because they give you very reliable data. The drawback, actually, as you know, is most of the components are abiotic, and so we need to figure out ways to build these systems which are friendly to the human body. Else, what we do with the pacemaker, right? You put a pacemaker in, you need to remove it to change the battery every 10 years or so, which requires surgery. So that's a procedure which you'd like to avoid. So what we're talking about are known as bioresorbable implants. That is, we want implants that can resolve in the body. Okay? And today, if you look at, again, what we use, the thread that is used to stitch you up after you have a surgery, etc. thread, that is bioresorbable. So it disappears. The body is able to decompose it. We want something to that effect when we design electronics in the body. So here's again some of the implants. So the way we will do a bio-inert implant is, again, you create an incision in the body, you stick the implant in. A bioresorbable implant would be essentially something which can get decomposed in the body. Ideally, we want something like this. We want an implant which is stuck into the body. It has an actuator, it has other circuit components, it has an energy device. What we want is for it to measure whatever the physiological quantities in the body, and is able to send it back through some sort of a wireless mechanism to a local computer, to a phone, whatever you have. And this process continues, and then this should be able to talk back to the sensor in case certain components need to be modified. So you want to have a closed loop system which can achieve completely hands-free control of electronics sitting inside the body. So let's talk a little bit about definitions when somebody reads about all these in literature. The first thing is biocompatible. What is biocompatible? Biocompatible is an implant that is able to be in contact with a biological system without causing any adverse effects. Biodegradable is something that should be decomposed by living organisms in the environment, like fungi or bacteria. And bioresorbable, which is of most interest to electrical engineers and medical practitioners, is substances that can degrade without any abnormal response in the human body. So the FDA have not come across rules in India yet, but the FDA in the US has very tight restrictions from what should be a bioresorbable to what should be a biocompatible. Again, this is an evolving process. As and when discoveries are made, I'm sure these lists will change. So an old work, for example, so this is a cochlear implant. So people who had lost the hearing in the ear, all this does is you're putting a flexible rod in the cochlea of the ear so as to transmit the sounds. So it converts the sound which is falling on the tympanum to the electrical signal connected to the auditory nerve. So this has been demonstrated using implants. So here is the cochlea. Now the challenge here is you have this very weird coil shape, right? So to put the implant in, so you need to first image it out, manufacture the right implant, and then stick it in. And we've had some people have had some success in getting people who had loss of hearing to be able to hear by sticking a sensor into the body. The other work that has been done is using nerve control. So today, especially these are for veterans who've been injured in war or in the army. Is there a way, by which we can electrically stimulate their muscles or electrically stimulate their limbs. And this can also be used when they're using artificial limbs. How do we connect the artificial limb to the certain nervous system? That we can also, these have been also proposed as pain relief mechanisms. If there's a way by which we can simulate signals so as to relieve pain, and that's for post-operative care, etc. Another application which is being popular is an insulin pump, and again, this is instead of supplying orally, this is being put inside the pancreas, and this can supply. Basically, it measures the glucose level in the body, and based on the glucose level, it activates the pump which is implanted inside and monitors the sugar. So this is a closed loop system where the sensor, once the glucose is measured, the system through the cell phone is able to modulate the insulin levels in the body, the sugar levels in the body. Another key area in this field is flexible electronics. Again, remember that most organs in the body are not flat or are not rectangles. So you want to have some sort of an electronic system that contours to the weird organ shapes, right? And so here's where something known as soft electronics, whereas these are either built on nylon sheets, they're built on silk or on plastic, right? And obviously plastic is something we can't use in the body, but silk has been proposed. And these things are able to contour to the organ and hence are able to give you the right response. So here is an example where they applied this. Now this is not implanted in the body, but this is a plastic this is a plastic network that has been contoured so these are sensors which are applied on the brain, right? And so by creating it on plastic, it ensures perfect contact with the cranium, and so you're able to get very good signal readouts out of this. So this shows a visual response that has been measured of the brain using flexible electronics when applied to the top of the cranium. Again, very interesting work, old work, but very interesting work. Using molybdenum sulfide and graphene, people have also tried to do optical imaging for human retinal implants. Again, this is something which has not been implemented yet, but this has been proposed. They put it on animals. And again, this consists of basically graphene transistors on a flexible sheet, and that has been proposed to be put inside the retina instead of the regular rods and cones that we have. And then that gives a response which is directly fed to the optical nerve. We also have applications in prosthetic skin, where basically you have a stretchable multi-electrode array which is set up on plastic, which can be directly put on top of the skin, right? And this is essentially used, especially in the case where people have lost their ability to move their limbs, right? So having something like this and able to simulate feeling or temperature, etc., directly from the artificial limb to the brain is something that can be achieved here. So this allows veterans to have a very normal life than what we have. So let's talk a little bit about bioresorbable materials. So what are the materials one has to think about when one is working in this field, right? So if you think about conductors, the key conductors, again, we have to move away from copper and aluminum because those are not bioresorbable. What are bioresorbable are magnesium and calcium, iron, zinc, molybdenum, tungsten. So you see that most of the electronics that has happened in this field, as shown in the next few slides, will use magnesium electrodes rather than copper or aluminum that we normally use. For semiconductors, again, ZNO, silicon has been proposed. There are options to use melanin, which is the pigment in the skin, and other organic compounds. And if you look at insulators, again, it's mostly silicon dioxide, silicon nitride, magnesium oxides, or any of the lipids that are available. Now again, with all this, it becomes very hard to characterize these. So if you look at some of these, so this is a great review article to read. But if you look at most of these publications, it's it's as an electrical engineer, it's very hard to break out data because most of the work is done by chemists or biologists. So it's hard to figure out, for example, what's the direction constant of this impedance. So here's some work where to do implants, organic semiconductors were used to fabricate devices, and here's an example of that using magnesium. And these were done using standard silicon wafer using MEMS processing. So these were for pressure sensors. So these were done directly on silicon, and then you release the silicon using your KOH process or DMH process, and then transfer it onto a PDMS stamp, and then use that to basically implant for local pressure sensors. We can also use inkjet printing to manufacture devices. Um, the performance is acceptable, however, better fabrication techniques need to be used. So here's an example of an implanted device. This is a transistor array which is being put inside simulated inside the human body. So here it's put in a lab in a beaker with organic liquids, and you see essentially that the transistor array begins to decompose and eventually uh, disappear in room temperature. So this is kind of the material you need to do implant electronics, where essentially beyond a certain time, the transistor and the material will disappear and naturally be absorbed into the body. An important um, component of these implantable electronics is energy sources, right? Because anytime, even a pacemaker, right? Pacemaker has a battery step under it. So the question is, are there better ways to make batteries? Right? So people have been working on this. Bioresorbable films like magnesium and molybdenum have been used to generate a battery. It has pretty low power density. So I mean, again, given that the application is for a week or a couple of weeks, which has to resolve again the application, it's pretty good numbers. They've also used certain organic compounds such as humic acid, etc., to report rechargeable batteries, again with a pretty respectable energy density. Okay, these are very seminal works done in this field. Okay, the point here is with the limited range of materials available. Typically, you could use lithium ion, but lithium ion cannot be used in the body. Lithium is poisonous. So you have to find a way to generate energy without using any of the materials normally used in our day-to-day electronics. You can also store energy using supercapacitors, and this is an example where people have used activated carbon electrodes to create supercapacitors, and they've also used water-soluble metal electrodes to do the same. Again, very respectable power densities have been demonstrated using supercapacitors. Again, I want to highlight the fact that the way you think about electronics in the implantable world is very different from the previous part of the talk, because here we're looking at things which will exist for more than for a week or more. Right? So we're not looking at, so it's a very different, we don't think about transistors as, okay, I just need to worry about it for a week and then I don't need to worry about that part anymore. But here, that's the challenge. We are looking at very, very short lifetime of these devices. So while it offers certain advantages, the bioresorbability becomes a big challenge. So therefore, it becomes harder to do these kinds of work. And then obviously you have energy transfer devices and harvesters. For example, people have used RF energy transfer using magnesium electrodes to transfer energy from the Wi-Fi to the sensor on the body. So remember, all this work again, I would like to highlight, has been done on sensors placed outside the body. People have still not identified this or integrated this with something which can be stuck inside. But these are all proofs of concept which have been done to transfer energy on systems on the body. Right? And it's a whole new challenge to figure out what's happening inside, because you have to worry about the impedance of the skin and of any other tissue that is inside. So especially for RF, right, you need to also worry about damage. Is there any energy damage which happens? Again, similarly, thin silicon microcells have been used to generate energy using photovoltaic. But again, that's something which has to be in the surface of the body, right? If you implant it, you're not going to get solar energy inside. And then an interesting work is essentially using magnesium zinc oxide stacks to build piezoelectric harvesters. And piezoelectric harvesters can be put in the limbs or can be put anywhere where there is bending, and that can be used to extract energy. So this is very interesting work, and there's some promising results from there. So here are some of the sensors that are available for temperature. Again, these are all being published, they're being tested in animals. Okay. So first one is a temperature sensor. So all of us know that the resistance of a material of a metal changes with temperature. So essentially it's basically made up of magnesium lines, if you will. And the reason we do these kind of weird funky features is because one, we want a lot of material, because that's when the resistance will respond. So you want a long line, but you don't want a large aspect ratio. Second thing, this has to be flexible, so this should be able to bend. So therefore, that's the reason why you see these funky images here. You want that so that it can be contourable and at the same time able to measure temperature. So you can see that the data is pretty nice. You get an accurate temperature measurement. So this is resistance as a function of temperature between 20 and 60 degrees centigrade. Again, this is for applications for human body, right? So you don't really need to measure temperatures beyond this range. And the beauty of this is this can be contoured to the organ. And the challenge there is how do you package this? You have to package this such that whatever outside is not impacting the temperature measurement. Similarly, pressure sensors using capacitances have been created again using iron magnesium plates, using an elastomer as a dielectric. And this shows the output of the voltage as a function of time, and this is the output. So this is used to measure the heart rate or the pulse rate, right, using the pressure sensor. Again, as I told you, this is being done outside, but you can think of this as eventually being implanted inside and actually used to measure pressure locally. So also pH sensors, as all of you know, pH is very indicative of physiological processes. So here there is a silicon nanoribbon transistor which was used to build a pH sensor, which is sensitive. So this is like any other biosensor. We essentially create the electronic component using the silicon device, and then we sensitize it using some of the bioactive compounds. Again, here you see magnesium basically part in most of the applications, and the pH changes surface charge and hence the transistor properties. So you see the sensor responding as the pH changes from 3 to 9, it goes from acidic to basic. And then we have, so there has been some very nice work done in developing a bioresorbable EEG sensor using silicon nanomaterials, and these have been used to record EEG signals up 33 days of surgery, right? And this again is used mostly for patient monitoring, etc. Again, this has been done on animals, not yet on human beings. So I just want to conclude this part with some findings. Integrated bioresource. So what we have seen so far in the literature is basically pH sensors, temperature sensors, sensors for various physiological components. But there is still, we haven't seen any targeted application. For example, suppose I want to create an entire system to track, say, a diabetes patient or to track AIDS patient, right? Those things have not yet been reported. We have not yet figured out, okay, what's the right system to build for monitoring or for recuperating or for recovery, target to a specific disease. So that is something which is still lacking because we don't have a lot of flexibility. And the other big thing is that, as I told you, most of this experimentation has been done on frogs, right, or rats. Large animals, there's been very little data, right? And humans, there is absolutely very little data. And obviously, that that needs to be done before any of this is taken seriously, because we don't even know what are all the biological hardens that we might have or compatibility issues. And so that, and even in humans, we don't really know how things will degrade. So that's again a very open question. So this is a field which is been active in medicine for quite some time, but I think a lot of electrical engineers are now getting into it. So it's challenging for us, but at the same time, it's something which we need a lot of collaboration with medicine to figure out what can be done, what cannot be done. So with that, I'll end my talk. Thank you for your time and thanks for your attention.
Any questions?
Yeah.
Neuromorphic computing. Sir, do you have exclusively neuromorphic processors?
We do have. There are available in the market. As I told you, they're built based. So if you look at NVIDIA, right? NVIDIA has it as built on top of the GPU. So it is available, but it's not built using embedded devices. So it's built using silicon.
What is the basis of the mathematical background? Like we use AMD with system cells with protein etc. are used. What is the mathematical basis of the neuromorphic?
So the mathematical, so if you write code, write a Python code, right? What you're implementing is essentially first that weighted sum and then a nonlinear function. So all that is just using a DSP. So I can implement the same thing on a DSP. The problem is that it takes a long time and a lot of power. The GPU is going to do that same thing quickly. That's all. So the NVIDIA structure of the GPU is not different. It's the same thing. Only thing it does much faster. So in that sense, it's a processor because it processes machine learning data, but it doesn't employ the neuron structure.
We don't require that much of clock, I think.
Clock is not important. Parallel processing is important. Actually, nowadays nobody requires clock, because clock is something which we are running behind and doesn't give any performance, right? Especially that's the reason why 10 years ago most of these processor people moved to multi-core. So with multi-core architecture, you're able to get a lot of operations per second without really going into clock. And clock impacts the local design, right? It impacts leakage power, it impacts capacitor power becomes very high. So clock is something you don't want to push as much as you. It's a huge power sink.
Sir, what type of activation function you use in neuromorphic design?
So typically there are standard functions like Google has sigmoid, ReLU, etc. So those are all used in software. What we do in hardware is we generally use an transistor in its semi-long, in its below VT to generate because you get that sharp combination of them. Today, if you look at the way people are publishing, right? I mean, it's very so in the university, it's very hard to create this entire processor from start to finish. So what people do is create the crossbars and then do the post-processing in software and then report results. So that's how they do. So what they do, even the nonlinear function, they implement in software. So they do the crossbar and then they send the output to an FPGA where they do all the stuff. So that's how it's published, but in reality, we have to do it using some sort of a device.
Sir, as we know in the hippocampus, all the memory is stored. So in Alzheimer's patients, there is a problem with the neuron. So is some work going on for the bioimpedance in the hippocampus?
I'm not aware of it. It might be, not aware. See, the brain, there's a lot of work going on, but yeah, I'm not aware of how they replace it. There is Alzheimer's and Parkinson's. There's a lot of work and there's a lot of funding also available, primarily because those are some of the debilitating diseases we have. But I'm not aware.
For this ligation depth, it's what is it? Lifetime.
Again, as I said, requirement is only 2 weeks, so you don't need to worry about lifetime. The problem is that in that 2 weeks, it is going to also erode. So you need to ensure that doesn't erode too much in the 2 weeks, but after that it's fine.
For using in pacemakers.
No pacemakers you want. I think pacemakers are very so. If you want to use a pacemaker goes for 10 years. That's not bioresorbable. That is actually implantable. And pacemaker today is so cheap that I don't think anybody could do this there. This is more for things you want to do quickly and you want to. It's mostly for patient recovery and monitoring. Nobody is planning to change the pacemaker. I haven't come across anything which says that pacemakers need to do this. Right then, thank you.
So now we'll be having our article discussions. And will we take a break at 12:30 for lunch?